Welcome to the webinar. We'll be talking about how you can use LabVIEW and Python together to solve engineering problems. So my name is Andrew Collette. I work at a company here in Austin called Enthought, and I'm sitting here at National Instruments with Colin Drawn, who's a software product manager. And so the agenda today is pretty straightforward. We're going to talk about what LabVIEW is and what Python is right up front, and spend a few minutes talking about this thing called the Python Integration Toolkit, which allows you to connect Python and LabVIEW together and solve problems. And then we'll zip straight into the live demos. We'll talk about how the toolkit works in the basic level, and then we'll show you guys how you can address a real engineering problem using Python and LabVIEW together. And then we'll show you guys at the end here how to take the application that you've developed and then deploy it using Application Builder, including both the LabVIEW components and the Python components. And so about the Q&A session here, we will actually be having live Q&A throughout the session. So in the chat window, you're welcome to ask any question you want, and we'll get back to you live as the webinar goes forward. And then at the very end, we'll have a few minutes to address some of the questions from the chat. So a little bit here about myself and about my background from Enthought. I'm actually trained as a laboratory research scientist and joined Enthought about 2 years ago. And Enthought is a really wonderful company for science and engineering problems. And so the company's been around for about 15 years now and kind of made our mark in the space of using Python as a platform to solve engineering and science problems. So we provide software, consulting, and training and support, all focused on the Python platform. And so we provide a number of Python software packages, including a full Python environment, an IDE for scientists and engineers with over 1 million downloads. And except we're headquartered here in Austin, Texas, and we have additional offices in Cambridge, UK, and India.
Yeah, hi, as Andrew mentioned, my name is Colin Drawn, and I'm a software product manager here at National Instruments. And there on the screen you can see our mission statement, so pretty aligned with Enthought's purpose as well, which is our intention is to equip engineers and scientists with systems that accelerate productivity, innovation, and discovery. And that includes a few different things. It includes a hardware platform for all of your data acquisition and testing needs, as well as a software platform that allows you to integrate nicely with that hardware and control and automate your processes. We're also based in Austin, and it's great to have Andrew here today to do the webinar. So part of that software platform that I mentioned, probably one of the key components is LabVIEW. So if you haven't used LabVIEW or heard about it before, it's an application development environment for designing and building out engineering applications. And so a key component of it is what we call the G language, or a graphical programming language for designing your logic and your systems. And we'll talk about kind of some more intricacies of LabVIEW moving forward, but the key point is listed there right under the LabVIEW icon. We want to integrate hardware, we want to visualize data, and then allow our users to accelerate engineering. And that has different tenets you can see there, like rapidly connecting to your instrumentation, which we have some on the desk today. Minimize your test sequence development time, quickly reuse existing code, as we'll talk about with the Python toolkit, and also visualizing results and reducing your deployment and rework costs as well.
Yeah, so you guys will see the visual aspect in the demos that we're going to do. It's really an amazing platform for developing interactive applications. So it's worth taking a few minutes to talk about what Python brings to the table. And so different aspects of Python have led to be used quite a bit recently in the science and engineering fields. And one is it's kind of obvious, but it's a high-level language, and so you're kind of freed from the details of having to compile, having to keep straight the various types and memory management and so forth. And another great thing about it is that because it's a general purpose language, it's used outside of just the science and engineering fields, we can take advantage of this huge ecosystem of software that exists for general purpose computing.
Right.
And that means things like web development, cloud computing, cloud storage, things like this.
Yeah, I think that last point is really key, because as we look at the software industry moving forward, no one company is going to be able to satisfy really all of your software needs. And so that's where we turn often to communities, such as either the LabVIEW community or the Python community, to develop and provide a lot of that analysis IP that we can bring into our applications. So a lot of that is what we'll talk through today, how we can use them together, I think, to benefit us rather than using them separately in independent processes.
Yeah, it's a wonderful point, and it really does kind of underscore this final point here, which is that One of the great benefits of Python is this enormous ecosystem of thousands of packages you can use. These come from industry, come from academia. They represent everything from how to read file formats to cutting-edge breakthroughs in AI research. It's all available to use immediately. So we'll change gears here a little bit and talk about this toolkit specifically. So the Python integration toolkit is our implementation or our solution to a problem that I had in my career before, which is that you have this wonderful LabVIEW ecosystem on one hand, which can talk to hardware, which can allow you to develop user interfaces and do rapid development. And on the other hand, you have the Python ecosystem that's based more along the lines of offline analysis. And so you might have scripts or modules that you'd run, packages you'd import to analyze data offline. And so you want to have kind of the best of both worlds here, but the question is how you combine them. Do you take Python and embed it in LabVIEW? Do you somehow take the LabVIEW environment and somehow embed it in Python? And so the solution that we ended up with here is more of a bridge. It's a live, seamless bridge that runs between an active LabVIEW process and an active Python process. And so they can share data, and both ends of the bridge can have their own ecosystems running in their own preferred way.
Yeah.
So on the Python side, you write or you reuse a small Python module that can be part of a big Python system. It can be part of an external library, something that you've written just on your own. And so you can use the entire modern Python toolchain. You can use the Python IDE, and we'll show you one that we use at Enthought called Canopy, debuggers, all the standard tooling. And the number one most important thing is that you can install packages from the ecosystem into that standard Python environment. So you can access the larger ecosystem of Python code. And of course, on the LabVIEW side of the bridge, it's all standard LabVIEW. And so we provide a number of sub-VIs that you can integrate into your LabVIEW application. And the Python module or Python script that you run runs in a separate process alongside LabVIEW, and then you can communicate with it seamlessly. And so you can call functions in Python, you can set and get variables, and the number one most important thing technologically is that we take care of all the gory details of data conversion. And so ordinarily, if you want to use an environment like Python with LabVIEW, you have to save to files, you have to do format conversion, you have to be very careful about how you store your waveforms and numbers and so forth. And so you can see over here on the screenshot that we have in the Python integration toolkit, basically you just wire your data straight into Python and it works. So rather than spend more time talking in abstract ways about what the toolkit is and how it works, I think the best thing to do is just to show you guys a live demo. And like I said, we'll start off with a hello world demo here, and then we'll move on to a more interesting real engineering problem. So I'm going to zoom over here to Windows. And I'm going to show you guys an example from the standard example library that comes with the toolkit. And so if you install the toolkit on your own, this entire example library comes through, and you can use the example finder or open it yourself. And so the example I'm going to show you guys is called Basic Math. And so here is the LabVIEW VI. So for folks who haven't used LabVIEW before, Colin, do you want to just talk about how the front panel works and so forth?
Sure, yeah. So Andrew just pulled up LabVIEW. What we're looking at right now is what we call the front panel. And that's where we design our user interface. So we have a drag and drop capability where we can put down controls and indicators to design kind of the front end of our application. And if you want to switch real quick to the block diagram, Andrew, we can just talk about that. So here's kind of the block diagram, which is where we design our logic. And as I mentioned previously, we use a graphical programming language that we call G to design kind of how our code should flow and how our data should flow through our function. And so now I think we can jump back to the front panel, and Andrew can talk about how we can augment this LabVIEW application using a LabVIEW script.
Yeah, so this is basically hello world for the toolkit. And so you have over here on the left-hand side of the screen, you have some data input. This is an array that we just programmed in here on the front panel. And what we're going to try and do with the toolkit is very difficult. We're going to try to square the number. We're going to try and just multiply it by itself and see what result we get. And so on the block diagram, you have this array over here as an input, and here it is. And so what we do is we launch a Python session. We call this sub-VI called new, and we point it at a Python module that I've written. And once that session is running, we now have live access to call functions in that module, to set and get variables and so forth. And so what we're going to do here is take that data, we're going to pack it so that it can be seen by Python, and then we're going to call a function in Python and return the result. And so an array goes in, we call the function, and an array comes out. And so before running this, I think it's worth taking a look at the actual Python code. And so here it is. This is the Canopy IDE that we use at Enthought. It's kind of like IDE optimized for scientists and engineers, and so it's got a debugger, but it's also got access to a package manager and stuff like that, so you can install Python packages very conveniently. And so in the Python module we have here, we have just one function. It's called square it. It takes an argument, and you'll notice that it just takes an ordinary Python argument. I don't have anything in here that is specific to LabVIEW. I don't have any kind of a wrapper or a binding that I have to write in order to communicate with LabVIEW. It's an ordinary Python function. It takes an argument. It prints some output, so we'll have a console pop up and see some output, and then it squares the thing and then it returns it. And so it's kind of a very basic numerical routine in Python.
Right, so for my Python application, I wouldn't have to change it at all.
That's exactly right. And so we can handle a wide variety of types, integers, floats, arrays of those kinds, Booleans, stuff like that. And so just about all of your ordinary Python analysis code will come over just fine.
Awesome.
And so I'll launch the front panel here, and so I'm going to run it now, and we're going to launch that session. And we're going to call the function, which will print some output, and then hopefully return a result we can use. So I'll run that, and there we go. And so it printed some output to the console, and we also returned an array from the Python function call, and we displayed it here on the front panel. Pretty straightforward.
Right. Yeah, nothing we couldn't do in LabVIEW, but I think what we're showing out here is how with a very simple interface we were able to offload that processing to Python. And then I think moving forward we'll show how we can make that more complex,
right,
for more complex systems.
Great. So should we move on to the hardware demo?
Sure. Yeah, let's
do that. Okay, so I'll close out of this VI.
Yeah. While Andrew's transitioning, I'll talk about the hardware system that we have in front of us. So me and Andrew are sitting here at a booth at National Instruments, and in front of us we have a compact data acquisition system, or a CDAC system if you're familiar with the NX hardware platform. And what the compact data acquisition system really is a chassis that houses different modules, and the different modules can allow us to do things like analog input, temperature input. Here we have an analog output module, and we have a analog input module to get accelerometer data. And so we have a sound and vibration signal simulator that's connected to our compact data acquisition system, and housed within that simulator is a balanced fan and an unbalanced fan. And using the analog output module from the compact data acquisition system, we can control the speed of the fan. So if we look at the VI that Andrew just pulled up, what we see here is on the left we have a graph that's going to show us the vibration. So if we run this, the analog output is controlling the balanced fan right now. So we see the vibration data coming in from our analog input module of the accelerometers on our signal simulator. And there on the right, we're actually doing a fast Fourier transform of that data to see if we see any spikes at certain frequencies. So if we're picking up any specific frequencies from the accelerometer data. What we can do is we can switch to the unbalanced fan. So I'm on the balanced fan right now. I'll switch over to the unbalanced fan. And you can see we see a spike in our vibration data, or our accelerometer data over time. And then also on the right, where we're doing our fast Fourier transform, we can see that there's a spike somewhere between 60 and 80 hertz of our frequency. And what we're going to do is we're going to augment our application to do some learning about what that frequency is and detect whether we are using the balanced or unbalanced fan. What we can do real quickly is switch over to the block diagram to just show how this is used in LabVIEW. So what we're doing here is we're using what we call the DAC-MX driver, or data acquisition measure experience driver, to control both our analog input and analog output modules. And so there you can see that we do the configuration, we do all the timing of the task, and then we start the task, and then in our while loop we both write to the analog output module and we read from the analog input module. And so that's really what's going on in the back end, is that we're controlling the fans, either balanced or unbalanced, and then we're getting back the data and doing some analysis on it. So I'm going to hand it over to Andrew now, who can talk about how we might augment that using Python.
Yeah, that's a great introduction. And so this little demo kit is a wonderful little self-contained engineering problem, I think. You've got two cases. You've got a low vibration case and you've got a high vibration case. And so the problem that we're going to address here is how you tell whether you're in one or the other. And so you can imagine this is kind of a hello world demo for a factory test condition. right? You've got some machinery that's exhibiting some vibration, and you want to tell whether it's in a good state or a bad state. And so the first thing that I do with this kind of data as a scientist, I see two different states over here that have different frequency behavior. And so before I do anything in kind of the real-time or the live system, I want to get that data into an analysis environment and do some analysis on it, and then see if I can come up with an algorithm that I think describes what's going on, and then see if it's pretty reproducible. And so what we've done actually is we've acquired some data from the VI here. Go ahead and stop it. And we put that data on disk, and so we have a Python module. I'll go over here to our demo folder and Python modules, vibration.py now, which is loaded up in Canopy. And I'll go ahead and make sure that we're in the right folder here so that we can actually access that data. There we go. So in vibration.py, I won't go through every detail, but I'll talk about what's going on. So basically, we have the problem of detecting whether or not we're in a high vibration or low vibration case. And so you could imagine taking that frequency vector that we saw, the power spectrum, and then trying to chop out certain frequencies and trying to do thresholding and seeing whether or not you have a frequency spike and so forth. And that's pretty much the traditional way that I would have done it when I was working in the lab. But there's an alternative, which is to use some modern machine learning technologies and then simply train it. So we have a data set of data acquired in the low vibration and high vibration cases. And we can use that those two data sets to actually train a machine learning algorithm to say good or bad. And the advantage of that, not only do you not have to sit down and programmatically develop some thresholding-based algorithm, also in the future, if the particular pattern of interest changes, if instead of having a spike at 60 to 80, I have one at 100 to 120, or whether I have harmonics or some other subtle vibration that I can see by eye on the plot, but I can't express in code, I can automatically retrain it, and it should work just fine. And so what I've done here in the Python module, I have an import statement at the very top of the file, where I'm using a Python library, a Python package called scikit-learn. This is one of the standard packages in the Python world for doing machine learning. And I have some code in here to clean up, to reduce my dimensionality of my data. And then I have a signal classifier class. And the process we go through is pretty straightforward. And actually, it's not that much code. It's about 100 lines of code, including all the debugging code. And so I have my algorithm up here, and I create a little classifier object. But of course, when you're doing this kind of work, you don't get the algorithm right the first time, and so you need to be able to iteratively develop on it. And so that's the great thing about this environment, is that you can develop your algorithm, and then you can simply run this Python module right here in the Canopy terminal and pop up some debugging information. So I'll do that. So I have a debugging block down here, which basically takes the data that I acquired from the VI and does the classification and then tests it on some test data. And so I'll run this, and it's going to print some output on the terminal over here. And so it tested some from the case that we know is the quote-unquote good vibration case, and so we see you have a bunch of positive numbers. And we have some very similar numbers over here for the negative, the bad vibration case. We also can do interactive plotting, and so one of the things that the algorithm does is it takes those frequency spectrums and projects them down from whatever it is, 1,000 frequencies, down to a two-dimensional space. And so you can see over here, this is kind of an arbitrary two-dimensional space, and we've sorted the points. And so you have the blue points are the low vibration case, and the red ones are the high vibration case. And so you can see that in the space we've constructed here, they sort out pretty well. You can see all the red ones are clustered over here, and all the blue ones are clustered over here, which means that with our machine learning tools, we can very easily divide the space in two and say, everything that's going to be on the top of the line is going to be a good case, and everything below that is going to be a bad case. And so this is a kind of interactive visualization that you can really use. It's very handy when you're developing your code.
Right. So I think what we're really showing off here is how we're getting the benefits of both. We're getting the benefits of the data acquisition from LabVIEW, and we're also getting some of the machine learning and analysis that we can do in Python. But notice we're using them in pretty independent, siloed ways right now. And so I think what we can do is show off how the toolkit can really merge those workflows and make it a lot more seamless.
That's exactly right. And so we've written this vibration.py module in a way that it can be used interactively, so you can put some test code from disk in there and then just see what the output is. But it's also written in a way that makes it very convenient to call from LabVIEW. you notice that there is this function, this method here called predict on our classifier object, and you give it a sample, an array of floating point numbers, for example, from an acquisition, and it returns you a single number that says whether or not it's good or bad. And so this is kind of tailor-made to be accessed from LabVIEW. And so I'll open up a different VI now, which is very similar to the one that you just saw, that Colin demoed. So this has also got the acquisition plot on the left over here, where it shows the acquisition from the fan and then the power spectrum over here. But this time, instead of just acquiring the data and saving it to disk and displaying it, we have got a connection to Python. Mm-hmm. And so you guys saw in the Hello World demo a minute ago how you can create a Python session, make some calls, and then discard it. And so if we go to, and the very last component that you need for this to work is some way to train the classifier. And so we could use the training data that we had saved to disk earlier in the form of the good and bad samples that we acquired earlier. What you'd like to do is to do the ability to retrain the system from the live data. That way, if you're changing your test harness, you're changing a different problem, you'll be able to retrain the classifier live. And so we have some buttons here for good and bad. And you push those, basically it acquires 100 samples or so from the input, sends them over to Python, and it retrains it live. And so we'll go ahead and give it a shot. Right now it hasn't been trained, so it's not producing any output. I got the fan here in the low vibration case, and so I'll acquire some data to do the good training set. It acquires pretty fast, and for completeness we'll do about 100 samples for this demo, right, for the good and bad.
Really good sample set.
Yeah. There we go. It's up to 99. And I'll switch over now to the unbalanced fan. This is going to be the high vibration case. You notice the frequency spectrum is going to change. I'll push the capture bad training button. And we'll acquire about another, so it's 100 samples of, I think it's 1,000 elements each.
Yeah, I think a key point here is you'll notice there's no delay in our system at all. So we're pretty much acquiring at the exact same rate, and you can see the indicator updating as we get every signal.
Right.
And that's what I found one of the most useful things about the toolkit is that because it's pulling up the Python session and keeping it open, it can do the really rapid data transfer that doesn't slow down the rest of my system at all. Right,
and so we'll retrain it. So we'll take the classifier and we'll put the new data we did. So this is promising so far. I got the needle over here on the left for the bad vibration. You notice the number is changing as the system makes predictions on a shot-by-shot basis. I'll change it over here to good, and it's over on the green. And so you can see, I go back to bad, and it's back to the bad. And so now, we're running the Python classifier in the background, and we're doing line classification.
Right. And this way, whenever our system changes, we can retrain it with the new data, and then our Python and LabVIEW code will adapt to that. And so that can be extremely useful if we want to do any kind of redundancy, for example, for our test harnesses, or we want to do any kind of predictive maintenance for our different systems that are running. So there's a lot of useful applications for this pretty simple demo we're doing here.
Great. I think that's a great point. And so I think we finished with the machine learning demo. And so the thing I'd like to show you guys next is once you've written, it has to do with application builder. And so once you've written an application like this, it runs beautifully, in LabVIEW, right, in the LabVIEW development system, and it also runs in the Python environment that you have on your system, right? And so this is running. I have the example of Canopy that's installed over here, right? So when I run the Python session, it runs from the version of Python that is provided by Canopy. And in fact, you can set that. You're not constrained to just use Canopy. In the tools menu over here, you can pick your default Python, right? And you can put whatever you want. But it is located, of course, in a Python installation on the computer. And so if you want to take this VI with the Python integration and then run it on a different system, say on the factory floor or a test lab, you can bundle up the LabVIEW component using a tool called Application Builder. But the question then is how you provide the Python environment. And so, in the past, if you want to do this kind of thing with Python, you get to install Python on every single machine that you want to use the thing on, and then you have to install the packages and so forth. And so what you really want is a way to bundle up both the LabVIEW and the Python code into one application at the same time. And so the current version of the toolkit actually lets you do that. And so in the tools menu, I'll go back to our engine vibration test here. And in the tools menu over here, you'll notice that in addition to picking your default Python, there's also an entry called Bundle Python for Deployment. And so if I select that, I get to export not only the Python interpreter itself and the standard library for the interpreter, but I can also pick a set of the third-party packages that I use to do my analysis. And so I'll pick an output folder over here, and I'll keep it simple, and I'll just pick the desktop. There we go. Select folder. I hit next. And now what's going on here is that we are attached to Python in the same way that we talked to it, in the demo here. And we have a listing over here on the left-hand side of all the various third-party packages that are provided in this Python environment. And there's things to do plotting, there's things that do data import, output, and then way down here, once we get down into the section that starts with S, there's one called scikit-learn. And this is the toolkit that we use to do the machine learning. And so you push this include button over here, and what that does is it brings into the distribution not only scikit-learn, but also this entire tree of dependencies. And so a top-level product like this depends on things to do numerical analysis, like I said, data I/O, things like that. And so we can specify our top-level dependencies and then pull in automatically everything we need into the environment.
Yeah, that's pretty powerful, and that's similar to what happens in Application Builder for LabVIEW as well, is it can find all the dependencies that we have.
Yeah, that's a great point. And so we'll let this run for a little bit. And so it takes a little bit of a long time for a demo, but we'll let it run in the background and talk about it a little bit. And so what's going on now is that we're using the kind of Enthought toolchain here, and we're creating a standalone Python environment that includes a variety of these different packages, including the Intel, MKL, fast math libraries. And we're going to create a little standalone environment and install a whole bunch of these different packages into it, and then zip it up and provide it as a standalone Python bundle. And so not only do you have the Python interpreter plus all the dependencies, it comes in kind of a compact form that you can then very easily integrate into a Python application builder, a LabVIEW application builder application. And so what happens, the output of this when it's finished is going to look like this. This is the demo folder that I had for the vibration test. And over here, there's a folder called Python Runtime. And in there, it's creating one on the desktop right now. But what's in there right now is basically a zip file that's got the entire Python runtime inside it, an extraction program, and then also some batch files you can use in your installer. And so I also have, as part of the code that we'll share with you guys at the end of the webinar, I actually have a LabVIEW project that includes both of these things over here. Close out of that, I'll open up the project. There we go. So here's the project. I have my engine vibration test machine learning, which is the VI that I showed you guys for talking to Python. And then the build specifications, I have a distribution for the application itself, and I also have an installer application. And so it's actually pretty simple to set these up. What you do is you specify that you want to include the Python runtime that I modeled. And then when you run the builds for these two things, you get outputs over here in the machine learning demo output folder. I'll get rid of that. And over here, you have an application that we built. So we have the app.exe, and you also have a bundled version of the runtime Python runtime. And you also have an installer. Here's the installer. And this is one of the standard installers provided by the Toolkit, by the NI toolchain. And so I've actually installed this application here on the machine. So I quit out of LabVIEW completely, just to make sure you guys can see what's going on. Out of that. So LabVIEW is not running anymore. Okay. And I've installed it here. It's an ordinary Python application, machine learning demo, ordinary Windows application, excuse me. I run that. And so this is basically the same VI that we had, only now, instead of running in a LabVIEW development environment, it's running as a standalone application, right?
Right.
And if I were to go to the folder where this thing lives, do properties over here, it's in C, program files x86, machine learning demo. And then here's the application, and then of course in the folder, a subfolder, here is the Enthought runtime. And so I got Python plus all the various dependencies that Python needs to operate, including the machine learning toolkit.
Yes, we actually just got a question on this.
Yeah, go ahead.
On the, can I use the Python integration toolkit in production environment? I think that's exactly kind of what we're showing here, which is you can bundle all this really nicely and deploy it to an end user or to a production system.
That's absolutely right. I mean, contact Enthought for licensing details on that, but it's absolutely what it's designed for. And so there is a concept of deployment within an organization where you have an application that you want to be repeatable, And so you don't want to run it in the development environment on all the various machines in the organization. You want to be able to deploy it. Mm-hmm. And there's also the concept of it being used as a component in if you develop a LabVIEW application to support, for example, a piece of hardware that you ship to a customer. You can augment that application with Python capabilities and then actually embed the Python integration toolkit plus the Python runtime packages in that application.
So we actually just got another question. What's the recommended RAM for this kind of application? So is the Python runtime, is that taking up a lot of memory space while running this?
Not really, and typically what you're going to find for that kind of application is that the data typically overwhelms the size of the Python runtime environment. And so just to be clear, I mean, it runs the toolkit when it's bundled up and running in a deployed fashion or in a development environment, does run on a Windows computer. But the memory requirements are quite low.
Okay, great.
Yeah. So that's great. That's through the end of the distribution demo, and so we have kind of a choice here. We can go to conclusion and Q&A and talk about that, or I can show one of the image analysis demos that I had from the examples.
Sure. I think the image analysis could be really interesting.
Yeah, I'll have to show that off. And so we'll go ahead and close out of this application. And so I mentioned before that you use these third-party toolkits to do Python packages rather to do analysis. And I showed you guys basically two VIs that have to do with numbers. And so in the first case we had an array that we were going to square, and in the second case we have some data coming in from a 1D digitizer acquiring floating point numbers and returning them to Python. You can also use LabVIEW and the LabVIEW toolchain, of course, to do image data. And so and one of the great things about Python is that you have the ability to use these third-party toolkits like OpenCV to do analysis of images. And so here is an example of one of those. I'll go ahead and open this up in Canopy. I'll show you guys the Python end of the toolchain first in this case. It'll be a little bit easier to understand, and then we'll go over to the LabVIEW VI and we'll show you that.
Sure.
This is a Python module that uses what's called the OpenCV or Open Computer Vision package for Python to do recognition of faces in a scene. And so this is an example of generic object recognition. It happens to be using faces right now. It's been trained on. But you can use this to basically, this technique to classify objects in a wide variety of scenes. And so I have a Python function here, in the same way that I had a function called, classify, called find faces. And at the input over here is an image. And it has some tuning parameters that you can set. There's a parameter for OpenCV for the fitting that, specifies the scaling factor for the algorithm and a few different smoothing parameters. And we import OpenCV on top of the file over here, right? Gives us access to import CV2, gives us access to the OpenCV library. And then we'll basically find the faces in the image. I think this version of it actually outlines the faces and then returns the entire image. But you can just as well return, a list of the rectangles where the images are in the faces are in the image. So I'll show you guys the LabVIEW end of this now. Let's see if we can find it. Image processing with OpenCV. Here we go. I'll load that up. And so this VI over here is very similar. Takes a JPEG file input, and then you'll notice that it has these parameters on the front panel that map to those parameters in the function. And so I can adjust, in real time, I can adjust the parameters for the nearest neighbors and the scaling. On the block diagram over here, it's very similar to the acquisition loop that you guys saw for the real-time demo for the vibration. We have go ahead and attach ourselves to the Python module, face.py in this case. We launch a Python session that runs alongside of LabVIEW. And then now we have an interactive analysis loop here where we can change the various parameters and then see in real time how the fitting changes. And so I'll go ahead and run that. It's going to use one of the images we have from the SciPy sprints. But we also do a great demo of this where we have a webcam running. Right. I don't think we have the hardware for the webcam on this, unfortunately. But you can see, we have a lab image loaded by LabVIEW that shows up over here, and we're finding all the faces in the image. And you can see that this particular algorithm is, was done in 5 minutes, and so it doesn't work super well for all the faces. But you can adjust the scaling parameters, right? And you can see as I do that, the live Python session alongside you, goes ahead and reevaluates it. And so you can basically, you can imagine this could be used to do webcam analysis or analysis of parts on a conveyor belt or what have you. And you can tune the Python algorithm over here from the LabVIEW interface directly.
Yeah, and we actually just got a question on this. Can we see the results from Python while LabVIEW is running? And so that's really what we're showing off here, which is our LabVIEW application is running and our Python code is running in parallel in a process. So really, that goes back to what Andrew talked about with the bridge. It's really just providing a bridge between the two. So we're getting pretty much real-time feedback from Python as it's doing its analysis.
Yeah, that's a great point. And we can actually reinforce that. We go over here to the block diagram, and we can actually modify this a bit. I can create a constant over here for the visibility, and you can show the console while it's running. And so you pop up a Python console now when you run the thing. And so this is the Python session we have running alongside. And I can even do stuff like, in the Python editor over here, this is find faces, and I can say, I can print faces. All right, I'll go ahead and save that. And I'll go back over here to my LabVIEW VI and I'll run it again. And there's the faces that it found. And I'll minimize this so we can still see it, and I'll run it alongside. I changed the scale parameter, right? It's going to change that, and it's going to print out a new output. And so it really kind of reinforces this idea that Python and LabVIEW, instead of it being an embedding or an alternative, it's kind of a live communication. It's a conversation between LabVIEW and Python.
Right. Yeah, I think that's really how you've enabled people to take advantage of the benefits of both, right? As LabVIEW can run independently of Python, they can run in parallel and communicate to each other when they need to, right? Because obviously there are some things we can keep completely in LabVIEW, some things we can keep completely in Python. And I think the key there is really the communication between the two.
And you get the sense right there what I just did of how easy it is to update your Python code.
Right.
And so you update it, you save the file, and then you reload it. And so one of the great things about Python and the Python integration toolkit is that the loop for development is very short. If you decide you want to make a change, it's very easy to do that and then see the results of the change right away.
Yeah, I think the debugging capabilities of LabVIEW combined with the debugging capabilities of Canopy especially allow us to really easily see what's going on between the two. And really this is the first I've seen of any of these types of solutions that gives us kind of that real-time feedback, real-time ability to update our system and see what's going on.
And one thing that I forgot to mention earlier, but we should bring it up, is that of course if you want to get access to a toolkit like scikit-learn or like the OpenCV image processing toolkit, you don't have to go out there on the internet and find it yourself. You can use the package manager that provides Canopy, and also other Python distributions have their own package managers. This is a very common thing nowadays. And so you can look at packages that are available. You want to install them, you click on them, and then you just install and they install. And they're available to be used, as soon as you install them, they're available to be used in the Python environment.
That's fantastic.
Great. Okay, well, let's go ahead and zoom back over here to the presentation. And I think we're just about at the end of the presentation. I do want to mention that the toolkit does have a free trial, a 30-day free trial. And we strongly encourage you guys to go and check it out. You can go to enthought.com, and it's linked off the homepage of enthought.com, or you can go to this URL here. That's direct. Also, if you're new to LabVIEW, check out ni.com/LabVIEW. There's a great introductory material on how to use LabVIEW. We are going to bundle up all the examples that we showed you guys today for the acquisition and so forth, and then send that out with the follow-up email to this webinar. Yeah. And of course, we're always happy to take questions. And so I think what we'll do now is we'll take a few questions from the chat session.
Yeah, I think we have a couple. One you touched on earlier was, do we have to use the Enthought Python session?
No, you don't. And so, I mean, we are very proud of Canopy. So we think it's a great solution for scientists and engineers, and it includes the runtime and the package manager and all this automation. But the toolkit is specifically designed to be compatible with Python from any vendor. And so you can use the standard Python distributions that you download from python.org, Canopy, third-party environments, whatever you want. Currently, it is the Python version is Python 2.7. Though we do have a roadmap for Python 3 support, and once that is in place, it will also support any vendor's Python 3. I will mention, however, that because the application builder functionality has to integrate very closely with the package manager, currently we only support preparing the application builder distributions from Canopy. We need to hook into various low-level parts of the package system.
Sure. And we had another question from Christopher Beard. He asked, I'm guessing that it does not support while true loops within Python, as LabVIEW would get stuck within Python. Is that correct?
Yeah, it is correct, except that you can get around it. So Python, the design of a toolkit is what's called synchronous. And so you make a function call or a method call from LabVIEW to Python, and then that LabVIEW thread will pause waiting for a result. But it's entirely thread safe, and so what you can do is launch a worker thread in Python that can take that calculation and do it in parallel. And I believe we have an example of how to do that in the standard examples for the toolkit.
Awesome. Thanks for the answer. We also got a question, can we call LabVIEW from Python? And I just want to make a quick plug for a toolkit or a library that we released called the Python LabVIEW Automation Library. And so that allows you to call LabVIEW VIs and pass parameters to them from Python. So I'll post that as an answer to the question now. Let's see, we have another one. Can a UI implemented in Python be called from LabVIEW?
Ooh, that's an interesting question. It's difficult because of the way that most GUI toolkits work in Python. To simultaneously display a UI and communicate with Python, because a lot of GUI toolkits require what's called the main thread. They run in the main thread,
right.
And so it's difficult to both run the toolkit and to run the Python server. There is, for things like the plot that I show, you can do stuff like that, because what you do basically is you do show, matplotlib.show for any matplotlib enthusiasts, which basically pauses the execution of the toolkit on the Python side and then passes it over to the GUI. And so if you want to use an interactive Python plot, you can do it that way. But the simultaneous use of the GUI toolkit and LabVIEW is problematic.
Right. Yeah, I think there's some caveats there where a lot of the GUI toolkits have blocking functions, and so you need to be very aware of where your code is going. And I think that's along the lines of another question we got. Are they running in different threads? Are LabVIEW and Python scripts running in different threads? And I'll pass that off to Andrew.
Yeah, it's a great question. And so the isolation actually is one step higher than that. We actually do process level isolation. And so Python and LabVIEW are actually running side by side in different processes. And so it's totally isolated, which means you can use different versions of LabVIEW, and so you're not limited to just 2015. You can use 15 or 2016 or future versions, and so it's very well isolated from that perspective.
Awesome. We got another one. Does the installer you run when deploying on a machine have to be rerun every time the Python code is changed? So every time I make an update to my Python function, do I need to update the whole installer, or is there just a certain module I can move over?
Oh, right, yeah. So there's basically, if you notice, actually I'll zoom right back over here in the UI to that deployment. There's a separation, so machine learning demo, between the Python modules and the Python runtime. And so you can export your runtime, as long as your requirements haven't changed, if you don't depend on any new toolkits, right? You can keep the distribution you prepared for Python runtime and just change the modules. Right, and so you're not at all required to go through the whole rebuild process every time you do that.
Awesome. I think we got a couple questions on Linux support or support for different operating systems, and I think right now we have some Windows dependencies. Is that right?
Yeah, I mean it is designed and tested on Windows. I mean there has been some interest in Linux and other operating systems, and so if you would like to vote for Linux support, I would love to hear from you.
Yeah. Thank you for all the questions. Would it be possible to call multiple Python scripts to run in parallel from LabVIEW?
Yeah, it's another great question. So you can have multiple independent Python sessions running, and so you're not limited to just one per global session per LabVIEW instance. I believe right now in the VIs themselves we're doing some serialization, so I don't know if you can do simultaneous function calls, but you absolutely can have multiple Python sessions open and active at the same time.
Right, and this was one of the most incredible realizations for me, is that parallel applications have always been pretty difficult in Python, and when combining them with LabVIEW, which has a graphical, very parallel-friendly interface, I think what you're really doing is you're allowing people to easily make parallel-running Python applications as well.
Yeah, absolutely, and it's all designed to be thread-safe, and so there's no problem whatsoever with having multiple Python sessions open. The only question is whether or not one will block the other.
Right, right. We got another question. What is the advantage of this toolbox versus just using a script node? And I think this is applying to LabPython, which was an open community-funded or based toolkit, which had a node which we could write Python scripts in. I think there's a lot of things that you can do extra with this toolkit that you couldn't do with the node. But
yeah, I mean it is very convenient for short Python functions. Absolutely, you have a little window in your block diagram, and you put in the Python code. The problem comes when you want to take advantage of the external Python toolchain, meaning the IDE, the editor, and also the Python environment into which you install these packages, right? And so instead of having an embedded Python system that runs within LabVIEW, we have access to a real independent Python distribution outside of LabVIEW. And so you could, for example, develop your code in Canopy and then paste it into a script node. But the block diagram itself is probably not a great environment in which to develop code.
Sure. That's a great point. I think we might have time for one more. We got a question. What about error handling? Do errors from Python pass to LabVIEW?
They do, actually, and the Python exceptions do pass over into LabVIEW, and I'll actually stop this and show you guys the palette here just for a second. I think it's under Add-ons, Python Integration Toolkit. And not only can you catch Python exceptions in LabVIEW, you can do it with a particular VI. And so we translate the Python exceptions to a standard set of LabVIEW side error codes. And so if you want to catch a Python exception by name, you can actually use a sub-VI to do that.
Yeah.
Okay. Well, I think that we're close to the end of the session here, and so probably we're going to sign off. Thanks again to everybody for signing on and watching the webinar, and we really appreciate it.